Okay, everyone, welcome to the 2013 final presentations for the astronomical observations, techniques, and instrumentation course. This is the first presentation. The speaker is Kevin Cooke. We'll be speaking about analysis of galaxy clusters using Sloan spectra. Kevin.
Thank you. So, the research that I did for this course centered on the spectra of known galaxy clusters that I had obtained earlier in the semester, and I had kind of developed a separate line of questioning for my own research for this course to analyze them, also see what kind of goes into the back end of these spectra. So the outline for this presentation is just a little bit of a refresher on the galaxies that I research, some of their characteristics, and why we consider these important. Then, where did I get my data? That's the Sloan Digital Sky Survey, and so I'll be talking about that, the telescope used for that, its years of operation. And then it gets into the details of how I tried to do analysis on these spectra using IRAF, and how eventually that did not come to that good of an end, but I do have results from the spectra through the SDSS, the display tool that I'll get into in the presentation. And all of this is to address the specific questions of, can we observe something called the red sequence from the total cluster redness? And I'll go into what is the red sequence, what is this used for, and how and why is it considered different to use it from the total redness instead of how it's actually used in previous studies, which is the redness of constituent galaxies in a galaxy cluster. With that, then I'll talk about a more specific analysis of one of the galaxies in my sample. So let's get started. The galaxies that we'll be talking about are elliptical galaxies. So this is a nice example that I always like using. And this is M89. You can see that it looks much different from the Milky Way because it does not have a disk structure visible. It kind of looks like it's its own just sphere. So it doesn't have a net angular momentum vector strong enough for everything to condense down into a disk structure. And so that means that these galaxies showcase a different type of behavior because you don't have everything compressed into a local area. What we expect from these is that there is a lack of cold dust in low redshift ellipticals. So at low redshift, they've already experienced a large amount of time in the universe, and their star formation has decreased significantly because they have run out of a supply of cold dust and gas. Any of the gas that is in the elliptical is actually kind of trapped in either this kind of high energy plasma that just has random orbits around the gravitational potential of the elliptical, and they just can't coalesce into any local area for star formation. Now, because of that decrease in star formation over time towards the recent period, it means that the redness, which this should actually say between visible, the green and red, that redness should increase with lower Z. So that I should have said lower Z there. So as they are closer to us in terms of time. So for example, if we have a low Z galaxy of like 0.17, that's only 1 or 2 billion years ago, and it's there that we can see that, okay, star formation just isn't happening like we see it happen in spirals. And we also expect to see little to no ionization emission lines because you don't have O and B stars forming. You're not going to have that many ionizing photon suppliers that you do in spirals. When you take spectra of a whole bunch of different galaxies, an easy way to tell kind of the difference between the ellipticals and the spirals in your sample is ellipticals will actually have a lot of absorption features from what kind of little gas that there is, and then the spirals will have emission from all of those star-forming regions. So the way that I looked at all these the galaxies in my sample was using the Sloan Digital Sky Survey, and this has actually been a survey that's been going on through different modes over the past 8 years. It centers on the visible, so it goes from 4,000 to 10,000 angstroms, and it covers a whole lot of the sky with 8,400 square degrees. My next slide is actually going to be the map over the sky that it covers, and you'll see just how huge that is. Because of how big of an area that this survey has analyzed, it's actually detected nearly 1 million galaxies and over 100,000 quasars, which are galaxies with active galactic nuclei. So that 8,400 square degrees is more than a quarter of the sky. They were able to take spectra for the objects that they detected. From those spectra, they can get redshift. From that redshift, you can say how far away these objects are, and that allows you to build a three-dimensional map over the sky that you're observing. So just like I promised, here's a picture. This is the southern galactic cap, so the southern sky, and then northern there on the right. So you can see just how much of the sky this survey has been able to map through its different years. And you can see the resolution of this survey by seeing a zoomed-in picture of M33, and I believe it's a star-forming region, NGC 694, all the way on the right. So this survey has a very good resolution for such a large-scale thing. So normally you expect, poor resolution for some kind of wide area survey. Now, the way they performed this was with its own dedicated telescope at the Apache Point Observatory in New Mexico. So it's a 2.5 meter telescope, 120 megapixels, and they had 5 different filters to measure the flux at these 5 colors. So they had blue, green, red, and then 2 near IR bands. I really like this picture because you can see that the telescope is actually weirdly shaped. The mirrors themselves are circular, but the casing is square, and it has this lotus covering that could open and close. As I said, this survey has gone on for, let's see, right, the 8-year mark was from the first 2 completed surveys, and right now they're in the middle of a third, which plans on finishing up next year. And the Sloan Digital Sky Survey was funded by the Sloan Foundation, which is a scientific foundation centered in New York.
Yeah, I have a quick question. Go back to the previous slide. And that's at Apache Point, right?
Yes.
And then go to the previous slide.
Did I?
And there's a strip of coverage near the south celestial pole. Is that true? Or is that galactic?
That's the galactic caps.
Okay.
So it is in southern, like Earth sky.
Yeah.
But because of the solar system's tilt with respect to the galaxy, you're able to get some of the southern galactic cap and some of the northern galactic cap. And a lot of the other money came from the NSF and the Department of Energy because they like science, and science is good. Now, when I got these spectra, my original plan was to analyze them using IRAF, which I'd heard about for a while as an astronomical analysis tool. And it has quite the learning curve because it doesn't, you have to start learning how to use Unix commands because that's what it's built in. And IRAF isn't exactly one specific program. It's actually a collection of different modules that fit together. So for example, there's lists, language, there's one from the NOAO, which kind of compilated all these different modules together, and in each of these modules you have different tasks that you can perform on your files. Now, because of the learning curve that I mentioned, there actually isn't that good of an error feedback when you do something wrong. It'll usually say like it can't read image or just undefined or something like that. I guess because of how this has grown from different pieces together, just the interface documentation for all of that isn't quite the best. And so there is a project going on called PyRaf, which can do a bunch of this in Python, which I do plan on learning eventually, either that or IDL as kind of alternatives to how to read these files. Now I keep mentioning files because the spectra that I get they aren't in a JPEG or anything convenient like that. They're actually in bits files, which are a specific type of storage file that we call multidimensional. So you can have like the file name and then like one, and so it'll take like the first layer of that file, or you could say two, take the second layer, and so you can put data in each of these different layers. So you can have, for example, like a table of X-ray data or a table of infrared data, and put those all together in a FITS file for storage and use later. Now, unfortunately, this is where some problems happened during the course of my research, because the Sloan Digital Sky Survey FITS files have a very specific way that they were stored. I'm still figuring out what exactly happened, but there's a specific module that you need to load in order to open an SDSS FITS file. And unfortunately, that module used to be already installed with IRAF in previous builds, and then in the most recent build, it wasn't there. And computers get angry if you try and have more than one kind of IRAF on, so I wasn't about to collapse everything by trying to load both. So my research started to take a turn towards, okay, as the Sloan Digital Sky Survey does have their own pages with interactive spectra, I'll use that for the steps of the study. And the study is going to be about something called the red sequence, that I mentioned in my intro. Now, when astronomers were trying to identify galaxy clusters, they kind of had a bunch of improvised detection techniques. One, for example, would be an overdensity of galaxies detected in a local area of the sky, saying, okay, since there's this local overdensity, it must be a cluster. But of course, that opens up the chance for error because you can have all these kinds of projection effects. And then you have to take redshift for each of them to check which actually do belong to the group. The red sequence uses the redness of the ellipticals in a cluster to measure whether or not the galaxies in a local area are a cluster. Now, let me just draw a drawing so that you can kind of conceptualize what's going on. So you have the center of your cluster. We'll call that a brightest cluster galaxy. You'll also hear the terminology most massive cluster galaxy. I've seen them used a bunch of different times. And then, I don't have blue here. Oh, well, green. Okay. So you'll have a bunch of different spirals also in your cluster. That's not what we're looking at today, but it's important that I use a different color for that. And then we have ellipticals that are within our cluster. So you'll notice I don't draw them with the spiral pattern. Now, what Mike Ladders and HKCE, who at the time worked at University of Toronto, found was that the ellipticals that are redder than the rest, that when you plot all these constituents on a color diagram, you'll actually see all of the ellipticals line up on a line. And then the different galaxies, such as the spirals, will actually be displaced on a different location. And I have a graph on the next slide that will be showing that to you. So my science question was, okay, since I have this total redness of the cluster, is it possible to say this red sequence with a sample of clusters at different redshifts, see if that total redness actually changes as predicted on this next graph. Now, a lot of this is whited out, but I'll unfurl it as I explain what's going on, because there is a lot on it. Now, let me walk over here. So, what we have is a color diagram with visible minus near infrared colors subtracted as our y-axis, and then we just have I-band for our x-axis. Now, when you do that, the ellipticals for a cluster would all kind of line up here on this line, and then any spirals you had would actually be below it, and then irregulars, which out of all the galaxies, there's only like 3% that are classified irregulars, would kind of be at the bottom. We're not worried about these right now. We're just looking at, okay, does this behavior of the ellipticals follow through if I look at a sample of clusters together? Now, this 0.1 is redshift. So that's where we would expect to see all these galaxy types at a redshift of 0.1. Now, if we try this for 0.2, you can see that the ellipticals become displaced upward on this color diagram. And their slopes are pretty much parallel. So that means that if you have like the redness of all the ellipticals, you plot them on a color diagram, you match it up with the lines from a graph just like this that's been calibrated for all this, you can use this as an indicator of redshift and as a sign that, okay, you do have a cluster. Now, when you, this graph does take this all the way to 1, and it becomes rather complicated. But you'll notice that the ellipticals, which are what I'm worried about, they keep getting displaced in regular intervals up on the color diagram. One thing that I'd like to look at in the future, and unfortunately they're still working on the data for this, is we can see a turnaround in these galaxy types, and it almost looks like if there was one for ellipticals, it would be up around like 1.2, but there just isn't. I haven't found enough data to say whether or not there's actually going to be a turnaround. Yep.
So what does each line correspond to exactly?
Each line corresponds to, so if you find a cluster, you take the redness from all the ellipticals in that cluster. They would actually be spread out on this line, okay, because each of the ellipticals are going to be subtly different, but they all share a common history of slowing down star formation and just being dust poor, and that ends up lining them all up on a line like this. Does that answer your question?
So each line is a cluster?
Sorry?
Each line is a different cluster?
Each line is where a cluster's ellipticals would be at different redshift. So at 0.1, all clusters actually show this trend. And that's why it's been sold as a cluster detection technique, because if you have like two different clusters, they'll actually both have ellipticals lining up on something like that. Does that clear it up? Okay. Now, what I did was I measured the redshift and then the redness of the different galaxy clusters in my sample. And this is my graph. And I'll be able to label some of these once I say what I did. So using SPSS, because of those different filters, you are able to see how much flux you're getting at each of those different colors. And what I found was, when I plotted them on a color diagram, what I am seeing is something very similar, in that as redshift increases, as redshift decreases, the redness is increasing because there's less of a difference between, in my case, the green and the red. So as we get to lower redshifts, the redness is increasing, which is what we thought to happen because of the slower star formation rates. Now, one thing that I was worried about with this is that I'm actually displaced a little bit, and I believe that this has to do with the color filters that I used. For example, if we go back to this, you'll notice that they used V minus I, and then my sample is going to be between 0.3 and 0.6. And what we expected was something in between like 1.4 and 2.3 on the y-axis. And when I plotted mine, it's actually much higher, which means that the galaxies are bluer, or greener in my case, than expected. And so that's something that I want to work on with future work. Because the discrepancy with my method and the actual red sequence method was I didn't measure the constituent ellipticals for each one of them. I used the total redness for the cluster, because the spirals should just be going at their normal star formation, destruction, star formation rate, and the ellipticals are the ones that are definitely going to be changing. So that's something that I want to look at. I also want to go further into the filters that were used, because when Gladders did his red sequence survey, he used, let's see, right, he used V minus I, and then I used G minus I, and that's definitely going to have an effect. Yes.
What's the difference between the G and V filters?
I believe that it's the specific location in the visible, because the G filter that I used was around 4770, and then I believe that the V filter that he used was closer to 5,000. So from what I've been able to read up on, I think that that's the biggest discrepancy between the two. And then and then projection effects, because the Gladders study, they were very, very careful to look for anything that could have been a projection effect, while I did not have enough experience on my own to look at, okay, is there anything in the way that I could like mask out and not have to worry about? Yep.
Projection of what?
Projection of other galaxies or stars near the field of view that could be contaminating the color.
Crowding.
Right.
Okay.
And so possible improvements on that are get more data on the clusters themselves, to do a much more higher resolution survey of that area, so to find those ellipticals, and don't waste time trying to learn IRAF when apparently the module that I need takes a whole lot to install. A big shout out to Sravning and Davide for telling me to use QFIT's view, because that was able to get me to look at these files when I really needed to. So with that general survey, I wanted to look at, okay, one of these galaxies I do have a really detailed spectra on. And so what's happening in these clusters? This is 1336 from the Sun Digital Sky Survey. You can almost see a bit of gravitational lensing here. And that's actually how it got into the sample that I recovered it from. Its Z is 0.1764. That's about 2.1 billion years ago. Now, when you recover a spectra from Sun Digital Sky Survey, what it'll have is the spectra with the best fit. And you'll notice that that is still kind of noisy. And when I looked into how they got this, that's actually after a lot of data reduction. So you can ask them for what the sky flux was, and what the galaxy was is down here, and then your sky flux is going to be all of these purple lines across the spectrum that needed to be subtracted out. So that also you can see how the sky flux starts to increase quite dramatically at the longer wavelengths. Now, with once they are able to do that sky subtraction, let's take a look back at our spectra. They're able to look at and identify emission lines. Right now they're just labeled blue, but on the next one there's like a finished product that properly labels what each of the elements are. And then once they have that final product to give to astronomers like me, you can start seeing what's going on. For example, what you should be looking at here is these oxygen lines, because ionized metals need something to ionize them, and very low star formation should not be doing that. What I said at the beginning of the presentation was ellipticals should have absorption features, which you can see in magnesium line right here. These emission features, however, are not expected to be there. And so, let's hope that the next slide works. Yes, it does, good. Okay, so because of that emission, you're able to take a ratio of that emission and plug it into something called a BPT diagram, which looks really complicated, but it just boils down to all these are H2 regions from local star formation that you would detect, for example, within the galaxy. Your active supermassive black holes, AGN, active galaxies are up here, and then low ionization emitting galaxies are down there. And when you take the measurement of 1336, you get a 0.46 for oxygen 3 over H beta, and that puts it down here, which it just says that we have some sort of low activity, whether it be star formation or a lowly active supermassive black hole that's ionizing oxygen 3, and that's the emission that we're seeing. So the final conclusion is that this is called a low ionization nuclear emitting region galaxy, a liner. My previous studies with the red sequence may be visible with like an average color for a cluster. However, there's still a large chance for error. And there are many different display tools for this that I should look into to continue my research in the future. So in thanks, say thank you to the Sloan Digital Sky Survey for doing so much great work. Thanks to IRAF for trying, and Gladders for actually developing this red sequence in the first place. And that's my presentation. Thank you for listening.
Okay, thank you, Kevin. I think we have time for some questions. Any questions?
Questions? Yes.
What was the main goal of the SDSS survey? Was it to find galaxies? Or just look at everything and see what we find?
I know that a lot of its, like its advertisement is like the number of galaxies that it found, but there are still tons of stars that it has been able to get spectra for in its database. So it is kind of a general survey with a general database that you're able to look for objects in. They just really sell the number count of galaxies because nearly 1 million galaxies. That sounds really cool, and there's so much that you can do with it.
Can you go back to the BPT diagram you showed?
Yes. Almost there. There we go.
So the O3 and H beta you got from the visible spectrum, right?
Yes.
Okay, good there. I just wanted to see what was on the other axis.
Yeah, unfortunately, I occasionally have problems with finding H alpha on some of these because of redshift moving H alpha out of visible. But since I know that I'm looking at galaxies, because they've been identified and I can see the picture of them, I know that I'm not looking at an H2 cloud within the galaxy.
So your red sequence.
Yes.
When you showed that plot that Gladders made, it was very nice and clean, and it had just nice lines. What's the characteristic noise of that? How thick are those lines actually supposed to be? Where can you have a galaxy's line on that you say, oh, this is still an elliptical? I guess.
Unfortunately, they don't have because you were kind of asking about error bars.
When you put
is.
a galaxy on there, where can you say that's still an elliptical galaxy that's not going to be?
Because the ellipticals are pretty tightly packed in, so I would say that the error bar would be 0.1 of this color spread across this. The spirals, though, whenever you look up papers of this, you'll see them kind of meandering around each other down here. It's the ellipticals that are quite a bit more predictable.
Okay. So you can plot the ellipticals with
Yeah.
pretty good regularity.
I have a couple questions.
Yes.
If you could go back to slide 12.
12. What slide am I on? Oh, here we go. 12. I think this. Yeah, this is slide 12. Which one
Okay.
are you looking at? Okay,
Yeah.
which one are you?
Yeah, that's fine. So the redder the galaxy, the bigger the V minus I, right?
The redder the galaxy. Well, what's happening is that since this is V minus I, as the galaxy becomes redder,
Well, hold on,
V
let's-
flux is becoming smaller, and so that the redder it is, the smaller this difference actually becomes.
The lower the number, the redder it is what you're saying.
Yes.
And the redder it is, the less flux in V, right?
Yes.
And the less flux in V, the higher the number is in magnitude, right?
Yes.
Therefore, redder is pointing up, right?
Redder. Because are you asking about like how red should be interpreted on this axis?
Is redder up or down on the vertical axis?
Redder is down. Because what you're having is this V is coming from new stars and star formation, and as that decreases, this V is actually was larger than I, and then is actually decreasing while I is staying relatively constant, and so the galaxy itself becomes redder in comparison between these two values as V decreases.
So that looks like a short wavelength waveband minus a longer wavelength waveband, is that right?
Yes.
Because I is sort of infrared, optical infrared.
Yeah.
And in that case, isn't it true that redder corresponds to a bigger number when you have a color? A short minus a long. Or to give an example, B minus V, or H minus K.
I know that
Okay,
okay, so
so-
they constructed this.
So something to think about.
Yeah.
Maybe you can go back and think about this because
It could have been whatever specific.
I had always
whatever
interpreted
filter
a
that they
higher,
used.
a larger number in color to be redder when there's a short wavelength waveband minus a long wavelength waveband because the lower flux, because magnitudes go up,
Yeah.
less flux, right? So that doesn't make sense to me.
I think that's because. Let's see.
Could have to do with AB magnitudes. You'd have to look into
Yeah.
that. So the next question is on slide 13.
So that should be the next one. With my results that are.
Okay, on slide 13, do you have AB magnitudes or are those non-AB?
I don't believe that they're AB. That could be another discrepancy that I have.
So that's an important thing to clarify.
Okay.
On slide 20, there's a spectrum, and it looks like that is an observed spectrum, so that corresponds to flux at the telescope, right?
Yes.
And so that's not de-reddened, or nothing's been done to that. That's the measured flux, is that correct?
For like reddening from the interstellar medium.
Yeah.
That I'm not sure. That's something that I do need to look up. That is a
Okay,
very
so here's
important
my question. If you look at that,
Yes.
and then imagine where the V band is, and
Yeah.
imagine where the G band is, can you point to where the V band is?
Their V band, they had at around 4770.
No, that's a G.
That's G.
That's
okay.
a gun G.
Yeah. Okay.
So where's the V band?
I thought that the V band was closer to 5,000.
So the V band's at 5,500,
Okay.
and if you walk over there at 5,500
Yeah.
and point at the flux, so it's like, I don't know, 20, 18, right?
Yeah. And
Okay, so the
yeah.
G band, where's the G band?
The G band is closer to the 7. No, wait. Oh no, I was thinking in
It's
front of you.
47, right?
Yeah, 47.
So
That's
go over,
what you said.
to 47, point at the
And
flux.
it's smaller.
Well, it's smaller, but how much smaller?
looks like around 47. So we're looking at like the difference between these two.
So 55, here's 55,
Yeah.
and here's 47. That's a factor of 2, right? So how many magnitudes is that?
A factor of 2.
Yeah.
That's, is that 2.5 log 2?
So it's big. It's big enough to make a big difference between data in G versus V, especially if it's AB.
Mm-hmm.
So you have huge variations in what you've done with the G and what they have plotted with the V, right?
Yeah, and I've
Maybe-
explained why all my stuff is displaced from.
Yeah, you could write this down, write down the math, and then see. And the other thing you can do is you get the filter transmission curves and you can involve them with the SED, and then you can find out exactly what the difference is. And that's trivial to do. It's very easy to do. Go to slide 20. That is slide 20, right?
Yes.
Okay, where? I can't see. Where's H alpha?
H alpha is right here.
Oh, okay.
Yes. So, unfortunately, for whatever reason, the telescope did not have spectra for that band. I know a bunch of my other galaxies had H alpha like over here, but for this one, it's supposed to be in there. But when you ask for that information, it isn't there. Actually, if I go back a few slides, you can see that that problem is still there. There's a gap in the information that they have.
Okay. And can you go to the slide 21? That's the following. There we go. So there's a little bit of sleight of hand here. You don't really know H alpha, right?
Right, so there is an uncertainty, like the x-axis, for example, I don't know. The reason that I can say that, okay, it's a liner galaxy is that these are all H2 regions from within the galaxy. All the extragalactic detections are over here. And there's a clear distinction between the two. And when I plot the 0.46, it comes
Right. You can almost guess what H alpha is by your analysis, right?
Yeah, you have to be in
Sort of in that
small
yeah.
area.
Yeah. Okay. Any other questions?
Is that true? I mean, if you have a lot of H2 regions, right? Can't you have a lot more H alpha flux? I mean, isn't this how you figure out where on the BPT diagram your thing belongs?
Like in a perfect world, you'd be able to detect O3, N2, H alpha, and H beta, and be able to get exactly on the graph that you're supposed to be.
Well, what I mean is, aren't you going backwards? Aren't you saying that liners live here, and so therefore, since this is a liner, it must be somewhere here? But isn't the use of the BPT diagram?
Well, I used the BPT diagram to find that it was a liner, because the difference between a liner and something that's extremely active up here is going to be the O3 and H beta amount, which is what I measured. So I was looking to see basically which of the two populations here this galaxy was, whether it was low ionization or it was a very active galaxy with an AGN.
But you just said you really don't have an X, so it could be anywhere along
This.
right? Yeah.
But that still does not include galaxies with AGN. You're not going to find them on this line.
Okay.
Okay. Well, why don't we thank Kevin again?